So picking up where we left off, on Wednesday, at the end of class, we were talking about radicals and roots. This is going to be a thread, again, that runs through our semester. We're going to meet it a couple more times, and each time we meet it, we're going to do a little bit more with it. So my main goal for our beginner level is to make sure that we all have an understanding of what roots and radicals are, what do they mean, and how do we plug in everything else that we know about algebra into working with roots. So just to get us warmed up on this, let me jump back into Alex and just pull, let's just pull this quick practice problem here. So just for a moment, where you're at, don't feel the need to work in teams on this one if you don't have time. Come up with a response to each of these two problems. So not using a calculator, evaluate each of the following, or if this doesn't evaluate to a real number, say so. So we get a little bit to talk about today about expressions that don't evaluate to real numbers, perhaps. Let's see if we can come up with an answer to each of these. Take about 90 seconds. Okay, so somebody want to volunteer an answer to this first prompt. So first, Christina, before you say what your answer is, tell us how you read this expression. So as in your mental narrative.
Negative
what does that sound?
1 times the square root of 64.
Yeah, that's a really good suggestion. So oftentimes the battle in an algebra problem is already lost by the time it crosses through your brain and you read it, right? And so making sure that you read things right in your brain is going to help you to understand them better when it comes onto paper. So I like the way that you said it here. You said that this is, first of all, taking that minus sign that's in the front of the radical and reimagining that as negative 1 multiplied by the square root of 64. And that's super helpful because now in this expression, what am I going to do first?
You're going to do 64 the square root, so that would be 8.
Yes.
And times negative 1 times a negative by itself.
Right. So you're absolutely right. And let me unpack what you said a little bit. So the first thing you said was, in this expression, the first thing I'm going to do is think about the square root of 64. Now, it's not immediately clear why we should do that first, right? In the order of operations, we don't have any guidance about radicals and roots. Right? All we have is parentheses, exponents, multiplication, division, addition, and subtraction, right? So one of the things that we need to do in order to figure out how to deal with radicals is figure out where in the order of operations radicals actually fit. And I agree with Christina. The first thing we want to do is take this radical, but where in this PEMDAS hierarchy do radicals belong? Well, kind of multiplication, but the problem with that is that if we think of it as a multiplication, then it has the same precedence as this multiplication sign right here, in between the negative 1 and the square root of 64. If we try to do that multiplication first, we may end up running into some problems.
We treat it as an exponent?
Yeah, exactly. There's the key. Radicals, the whole purpose of a radical's existence is to be like an exponent. In fact, to be exactly the opposite of an exponent. If we were being really truthful here, in our order of operations, we know where multiplication belongs because we know where division belongs. Maybe I should say that the other way. We know where division belongs in the order of operations because it's exactly the opposite of multiplication. And so division and multiplication have the same precedence in the order of operations because they're the same operation, just turned on its head. Same thing with addition and subtraction. Subtraction has the same precedence as addition because they're just inverse operations to one another. Well, radicals and roots are just the inverse operation of an exponent. And so they take the same precedence as exponents do. In fact, even more is true, as Christina just mentioned. It's true that every radical can be rewritten as an exponent instead. This is what we talked about last time. So let's just take a moment. I'm going to fill in the rest of the work that Christina suggested up here, so let's do that. Negative 1 times the square root of 64, that's negative 1 times 8, and then negative 1 times 8 is negative 8. Okay, now let's fill in. Why is it that we can treat the square root of 64 like an exponent? So what exponential expression is equivalent to the square root of 64? 64 raised to what power?
It'd be 8 with the power of 2.
It would be, okay, right? So last time we talked about the fact that we know what the square root of 64 is because we know 64 is equal to 8 to the power 2. right? Okay, but the problem with this is, as I've written it here, I have something that's untrue, right? What I wrote here is the square root of 64 equals 64, which I don't think that's true. I think this equal sign right here is something I don't want. So what I'm asking here, and this is sort of the second goal that I have in our talking today about radicals and exponents one more time, is I want to, again, remember what we talked about on Wednesday, which was, because I know that 64 is equal to 8 to the power 2, that gives me a way to rewrite the square root of 64. And we decided the square root of 64 was 8. Right? That's what you used in your calculation just now. But I want to rewrite the square root of 64, which is what we would have on the left-hand side of this expression, as 64 raised to some power. So the question is, what power do I need right here that's going to convey the same meaning, the same information, as taking the square root of 64? 1 over 2, exactly. This is what we talked about last time. And the reason for that is that raising the right-hand side of this expression to the power 1 over 2 is exactly how I can cancel that exponent, right? The exponent right here, this exponent of 2. If I want to cancel that exponent, what I need is I need to multiply that exponent by 1/2. Well, how do we multiply exponents? We raise a power to a power. That's what we were talking about a week ago, right? When do we multiply exponents? When we raise a power to a power. So if I raise this power to a power, then I can multiply those exponents, and 2 times 1/2 is going to give me 1, which is the exponent that we don't need to write if we don't want to. But if I do it to one side, I also have to do it to the other side of this equation. And so on the left-hand side, I raise 64 to the 1/2 power. So this is something you can take to the bank. If you remember nothing else from this conversation, remember that the square root of something, no matter what, is underneath this radical sign, is the same thing as that number raised to the 1/2 power. So this is the most basic conversion of a radical expression into an exponent expression. So not only do radicals have the same precedence because they're the inverses of exponentials, in fact, every radical is equivalent to an exponential. Just by taking the index of the radical, which for a square root we don't write, but it's secretly a 2, hiding right there, that I just wrote, but you couldn't see it. Let me try that again. Secretly, there's a little index of 2 inside of this radical. And the reason that index of 2 is there is because it conveys the information that's in the denominator of this fraction, this 1/2 power, because the square root of something is that number which, when raised to the 2 power, gives me that quantity. So anytime you see a square root, you can just rewrite it as a power of 1/2. This is a calculus key right here. This is something that, if you remember this in calculus, let me put it this way, if you forget this in calculus, you're going to have a bad time. But hang on to this, because this is super useful, because it's much, much easier to do algebra with an expression that's written in an exponential form than it is to do algebra with something written in a radical form. So get comfortable with that conversion. We'll do some more examples of that in a little bit. So now tell me, what's different about the second example? Ready? Yeah, so the big difference here on the second example is that the negative is underneath the radical. So that's the difference that we can see. So, okay, how did that change the work that you did in this example? Okay, why not? What do you mean? All right, so right off the bat, so Brittany looks at this and says, so red flags immediately go up for you, right? And you write something like, we can't do this. Or what if you're working this problem in ALEKS, or if you're looking at the instructions that are sort of printed on the screen up here, you might write this as not a real number. Okay, so let's talk about that, because we've got to have a pretty strong argument on our side to stop in the middle of doing an arithmetic problem and say, this answer isn't even real. Well, what does that mean? Yeah, Jerry.
There isn't a number that's squared and become a negative.
Yeah, exactly. Okay, so that's a very careful and absolutely correct statement that you just said. There is no real number which, when squared, becomes negative. No real number becomes negative when squared. Why not? How do we know that's true?
Because it becomes a positive.
Okay. Becomes English when squared. Okay. Does it always become a positive? I'm going to be a little bit pedantic here for a second. Is there any real number which is not positive after you square it? So let's say I take a positive number like 7. If I square 7, well, what does it mean to square something? It means multiply it by itself. And so if I multiply 7 by itself, I get 49. That's positive. If I take a negative number, say I take negative 7, and I square it, what happens? Yeah, so the secret here is that when I square something, I multiply it by itself, and if it is positive, then I get positive times positive, which is positive. But if it is negative, as it is here, then when I square it, I get a negative multiplied by a negative, but a negative multiplied by a negative is also positive. I'm still going to be pedantic and claim that there is a number out there which has a square that's not positive. There's only one number whose square is not positive. Zero is the one number whose square is not positive, because what is the square of 0? 0. And 0 is not a positive number, nor is it a negative number, right? It's the one real number which is neither positive nor negative. But the point is that the real numbers are such that we can't multiply anything by itself and get a negative answer. So no real number becomes negative when you square it. That means that if I try to take the square root of negative 25, that number can't possibly exist. Right? That real number, I should be really careful here, that real number can't possibly exist. So if we want to take the square root of negative 25, we in fact have to invent a whole new system of numbers in which to do such a thing, which is not something we're going to do in our class. You might see it in calculus later on. You might not. Some calculus courses use it, some calculus courses don't touch it. But for our sake, let me go back to Jerry's comment. How are we going to know when we're evaluating a radical to just stop and put down our pencils and say the answer is not real? What's your cue, your mental cue?
When the negative is underneath the radical.
When there is a negative quantity underneath the radical, exactly. So anytime there's a negative quantity underneath a radical, square root of a negative means you can stop right there. Square root of a negative is not real. Okay.